All right, welcome back to Combustion Chemistry, Part 4. So today, we'll start out by talking about accuracy, error bars, uncertainty representations, because I think you should have gotten the message from the previous lectures that we have a lot of numbers in these models, and we don't know any of the numbers really that precisely. And so keeping track of what the uncertainty is a really big deal. And also, as we're trying to improve the accuracy of the numbers, you have to understand what your current error bar is. And a concept that comes up in that is whether the numbers are evaluated or not. So you saw this a little bit with the thermochemistry. That with the thermochemistry, there's a UPAC committee. UPAC is the International Union of Pure and Applied Chemistry. And they formed a committee to sort of double check thermochemistry numbers and try to get the international consensus on exactly what the accuracy is and what the numbers should be. And those are called evaluation committees. So they try to look at everything that's known about a certain number and try to establish what's the accepted value. There's a similar thing called co-data. You guys might have seen it. It has things like the mass of the electron and the value of Planck's constant, stuff like that. So there's a whole committee that tries to evaluate from all the information we have what's our best numbers for these important numbers. So there's a similar thing happening in kinetics, and they're called the evaluation committees who try to evaluate the values of the rate coefficients and figure out what we really know about them. And then after finishing talking about that, I'm going to start talking about how you pull together all these reactions into reaction mechanisms, how they're constructed, how sensitivity analysis and uncertainty propagation are relevant to the construction of the mechanisms, and the improvement in the mechanisms. A thing called flux analysis that's useful to help you understand a complicated mechanism. And then what can you learn by comparing the predictions with experiments and what you should do. Because when you compare a prediction of a model with an experiment, invariably they don't agree. And so you have to figure out what then? What will you do? All right. So the review of the previous lectures. First is that the liquid fuels are the best energy carriers, but most of the current liquid fuels come from fossil fuels, and so they contribute to climate change. And there's a bunch of other side issues about price and local pollution and things, availability, stuff like that, that are also very important. So we would like to have predictive models for the combustion chemistry of the different fuels that we could use for design of better engines and better fuels. And maybe ultimately for co-optimization of the engine fuel system to make the most optimal system. The chemistry models require lots of thermochemistry values and rate coefficients. And so a big part of the effort of combustion chemistry is trying to get those numbers, which are required for the models. We can measure the thermo and some of the rate coefficients very accurately, but we need a lot more numbers than we can actually measure on any practical time scale. And some numbers are very difficult to measure. It's hard to devise an experiment that will unambiguously measure the thing you want because of various interferences and problems. Also very difficult sometimes to reach the conditions that you care about it. And so many of these numbers are functions of temperature, and some are also functions of pressure. And so you can measure them in some temperature range, but you always end up doing extrapolations into regions where you really don't know what the number is. And so that introduces more error. We can roughly estimate most of the thermochemical numbers we need very quickly using group contribution methods. And so if you wanted just a first guess at the thermochemical values, you can get a pretty good first guess. And actually, for a lot of the rate coefficients, you can also get a pretty good first guess. Maybe we'll talk more about that later today. But they're not that accurate. And so you have to ask, well, are they really accurate enough or not? You can also, instead, you can try to go from first principles and use quantum chemistry and statistical mechanics to try to calculate the thermochemistry and the rate coefficients. And this is accurate enough, for sure it's accurate enough to be useful, but it's definitely not perfect. And there's a lot of approximations involved in those calculations. I highlighted some of them in our discussions. And there's a kind of ongoing research effort to try to reduce the size of those errors, to try to make them more accurate. But currently, you have, the experimental numbers are usually the best. A little bit worse are the quantum chemistry numbers, and then worse than that are the group contribution and analogy rules. But of course, it's inverse for how much effort's involved. So you can calculate all your numbers you need in 1 hour with the group contribution methods. Maybe you can do one number in 1 hour with quantum chemistry. Maybe you can do one number in 1 month with experimental work. So that's the sort of situation. All right, so a critical question is, how accurate do we need to be? And I think that it depends a lot on the application. So when I worked in industry, the models weren't any good in general. Back then, it was the 90s. But the models were still very valuable. And that was because having a model that's even semi-quantitative, even qualitative, having the right cartoon of what's happening in some phenomenon is very helpful to the experimentalists to try to guide them to make good choices of what experiment to do next. And actually, a big part of experimental work, when it's exploratory, is just trying to get the right cartoon, the right rough idea of what the phenomenon is about. And then you can then devise experiments to actually try to make that quantitative understanding. And so the models that you can build for combustion chemistry right now, in almost every case, are even better than qualitative. They're at least semi-quantitative. And so they're really very good for the kind of get the rough idea of what's going on type purpose. And so that's one of the reasons why they're very popular. Actually, I don't know if any of you pay attention, but in the heterogeneous catalysis community, there's a huge amount of effort going on doing computational catalysis. And there's gigantic groups of people calculating every different possible catalyst and all the different reactions. And those models actually are very poor quantitative predictive power. But for the first time, people have a cartoon picture that has some basis. Whereas before, people wrote like, then a miracle occurred. Right, with the catalyst. It was like, they called it magic foo-foo dust, is what they used to call it when I was in working for Exxon. We want this reaction to occur, we sprinkle in some magic foo-foo dust, and then magically it occurs. And it doesn't give you much guidance about how to make the next foo-foo dust if you have no idea how the last one worked. So having a model at all that's at all telling you about what some important reactions are and some important steps and important intermediates is very helpful to the chemists to get some idea of what they should do. Before they would do, actually, they called it combinatorial catalysis, where they just had robots try to synthesize every possible catalyst and automatically run as many tests as they could because they had no idea. But people, I think, overall decided it's a lot better to not do that. It's better to actually understand, at least roughly understand what you're doing. And you can really guide the experiments to be more focused instead of just randomly trying everything. Then what other purpose do we have when we make the predictions? So, I mean, you think in the ultimate case, you really predict everything perfectly. You put the whole thing inside a computer program, tell it to optimize your design. It would tell you exactly, exactly how to design your piston bowl, and it'll tell you exactly what the fuel injector pressure should be. And you don't have to do any work at all. Right? So the engine guys would love that, right? Or you tell the refinery, mix exactly 22.3% of this stream and 14.7% of that stream, and you'll get exactly the combustion properties you want. But I think we're way far from that. So we're at the point where we're going from qualitative into quantitative, and for some things we're quantitative, but you'll see some of them are not. And for the ones where we're not quantitative, we're still trying to figure out exactly what's wrong. What's wrong with our models? Why aren't they quantitative? So and we're still learning new things about the chemistry. So there's you'll see, there's some things we can do really well, and some things we can't. We're sort of like this intermediate regime right now. But anyway, it's an important thing to keep in mind is reducing error bars costs money, costs time, costs effort. And you have to figure out, how much time and effort are you willing to put into reducing an error bar? And which ones do you really care about reducing? And how small does it have to be before it's useful to you? And this gives the idea of successive refinement. Do you guys have this idea? Where you have a first zero-order picture of something, and then you refine it a little bit, get a little bit better picture. And then, if you really care, you put some more effort and try to get an even more detailed picture. So that's exactly the kind of stage we are with this. And it's not just with the combustion chemistry part. Also in the CFD, there's a whole series of things you can do. Like, for example, you can do a RANS calculation. It's very easy, but it's not really right. So then you might try to do some, simplistic, I don't know, what do you call it, eddy dissipation concept, or there's these different like sort of rough models of what the turbulence can do that's a little bit better than RANDS. And then, if you're really into it, you might try to do LES, and there's probably 47 flavors of LES, right? And then if it's life or death for the future of the free world depends on it, then you get them to give you all the supercomputers, and you crunch out a DNS for the system, right? So it's very much similar with the combustion chemistry. And the uncertainties in the chemistry mostly come from the uncertainties in the rate coefficients in the thermochemistry. And so we have to figure out sort of what accuracy, we decide what accuracy we want in the final model, then we have to decide what accuracy corresponds to it. How accurate do the different Ks have to be in order to achieve that accuracy? And just to keep in mind, garbage in, garbage out. So if you put some completely stupid rate coefficient into your model, then of course you'll get some completely stupid prediction out. And I think this whole topic is being discussed, but is not science yet. So there's a big discussion in this community and in the Department of Energy community more generally is about uncertainty quantification, trying to figure out how to deal with error bars in some quantitative way. Historically, we have not, as a community, done very well with this, and actually most fields do not do such a good job with error bars and uncertainty. We mostly just try to find a number. We want to know the mass of the electron. I don't know what the error bar is in the mass of the electron. I don't know if you guys know either, right? We just don't pay attention to it. We just use the number as if it's perfect, right? And so that's normally the way we proceed. But if you're more sophisticated, you should always think, of course, my experiment is not perfect, and of course, the model prediction is not perfect, and of course, they have error bars, and I really need to know about that. But we don't have the software, the tools, the thought mindset to focus on the error bars as the important thing. Anyway, so this is really not resolved, and probably you guys in your generation will be the ones that figure out how to do this in a kind of efficient, become normal practice. Right now, it's like a few people have done some example calculations, so you can do uncertainty propagation. They've done a few example calculations, of some methods of how to do it, but it's like not routine. When I review journal papers, many, many times, there would not be a single error bar in the entire paper, and many of those papers are accepted. So it's not, people have the idea, it would be a good idea to know the error bars, but it hasn't become part of our DNA. We're not always doing error bars yet. And often, if there are error bars in the journal paper, my experience is that oftentimes they're not accurate. So there might be some simple formula you can use that calculates something, and the student wrote the paper, just sticks it in as error bar, but may have no relation to actually how uncertain the real number is. And the way you know this is that subsequent people will then remeasure, say, the same quantity. They'll often disagree way outside the quoted error bars. Actually, I have a funny story to tell about this. So there's a molecule, CH2OO. And this was hypothesized a long time ago. It's called the Kriege intermediate. And molecules like this are formed whenever you have ozone. And so we have a lot of ozone around in the smog and also up in the stratosphere. So these molecules are being formed a lot. However, they're really hard to detect because they're super reactive, because it's kind of strange. It's a diradical. So it has an electron over here, and it has an odd electron on this side, too. So it's kind of a weird molecule. So anyway, a couple years ago, somebody found a convenient way to make a pretty high concentration of these radicals, and also a spectroscopic way to probe them. And so I happened to have a laser that had the right wavelength that corresponded to the spectroscopic line they had discovered. So I said, hey, I'll measure it. So I had my students make some of this radical and measure it. And the first thing you do when you make a radical is you measure how it recombines with itself. So all the radicals, if you make radicals, they're unstable, and almost all of them want to dimerize. And so you make some, and you see how they go away. And then you put some other stuff in and see how it reacts to this stuff a little bit later. So we did that. We measured it going away. And so my student said, well, we have this rate coefficient for this going away, so let's just publish that. And I said, OK, sure. I wasn't really that excited about it, but it's OK. You measure the number. It was in the normal range of how fast things diffuse together. So it looked OK. And just as we were doing that, one of the students involved is a literature search, and there's a new paper coming out in Nature Chemistry says the unusual rate coefficient for this reaction. And their number was like an order of magnitude bigger than our number. And their error bar was only like a factor of 2. So they were, our measurements disagreed way outside the error bars. And so we did a lot of double checks, and it's like, I'm pretty sure our number's right. So then I wrote an email to the professor involved in the other paper. I said, we really think it's this number, and we explained why we think we had it right. It's a second order reaction, so you have to do calibration, so it's a little bit complicated of how to do it. So we'd explain the whole calibration procedure, but I was pretty sure we did everything right. So I explained it to him, and the guy wrote back and said, yeah, I think you're right. And yeah, actually we're going to change our whole way of doing the calibrations and stuff, because the way we did it, we've decided probably something's wrong with it. But so he hit a paper. It's in Nature Chemistry. It's a pretty big journal that has the wrong number. The title of the paper is telling you it's the wrong number. It's telling you the unusual rate coefficient measured for this thing. It's actually the wrong rate coefficient for this thing. But of course, because it was unusual, it got accepted in Nature Chemistry. If I submitted my paper to Nature Chemistry, they say, "What's the big whoop? It's the number you'd expect, right? Why is that exciting enough to be published in Nature?" So anyway, this is just a problem with the way the science is and the way our field is that the people who did the review on that obviously didn't do it carefully enough to figure out what the problem was with the calibration procedure. The error bar they quote had like no basis in reality because the whole number is completely wrong. So they're nowhere near, the error bars wildly underestimate what the real error bar was. But the way the system works, no one really cares about error bars. And so no one really cares, and they like things to be new and exciting. So some really weird numbers are exciting, so they publish it as the weird number in the big journal. And then everybody has to read my paper, coming out 2 months later, and says, actually, that number is completely wrong. And the professor, we will write a sentence in the paper saying, by private communication with the professor, he agrees that the previous number is completely wrong. Anyway, that's the situation. Is that the experiments are not perfect, and it's really actually the experiments are usually pretty good. It's the interpretation of what the experimental signals mean. Usually, you have to have some model, and unfortunately, people believe the simple model that's used. Whereas the real signals, every real phenomenon that's happening is showing up in the real signal, and if you only put a little truncated model, and then you would vary some parameters in that model to try to make it fit. If you can achieve a fit, you think you're right. But of course, you freely adjusted the parameters. They don't have to be at their physical values anymore because you're compensating for everything you left out of the model. So anyway, so there's a kind of a work ongoing, and maybe you guys can help with this, is to try to get people to actually report the data. So in that paper, for example, he just reports the number of the rate coefficient. I think he shows one representative data trace. But he doesn't actually report what he measured. So it's not possible for anybody to go back and reanalyze the data and extract the real numbers out of it. And this is very common. It's not just one guy. I mean, it's all over the place that people don't usually report all their data. At best, it might be in somebody's PhD thesis. But even then, maybe not. Very commonly, it's on some computer disk attached to the instrument that made the measurements as the raw data, and then when that computer fails and they throw it away, the data's gone. And so we, as a community, don't do a good job of keeping track of the raw data, so that when you go back and you want to reinterpret some previous experiment, by the time you get to it, very often there's no way, nobody has the data anymore. So that data is like ephemeral, it's just gone. And all you have is some constants that they interpreted, some results they interpreted from the data they had at that time. And they use the best knowledge at the time, usually, to try to do the extraction. But if knowledge changes later, their interpretation might be completely wrong. And then the whole thing is basically you have to reproduce the entire experiment if you want to try to get the number again. So there's several of the editors of the journals have gotten together and trying to persuade the authors to include all the raw data in the supporting information, in the electronic supporting information in the back, so that there would be a permanent electronic archive of the actual data, and that way it'd be possible for somebody to go back and reinterpret data. But there's a lot of sociological resistance to this. So people, every time you measure data, of course there's some trace that has some goofy glitch in it. Something funny happened. You know, a guy came in and opened a soda and spilled the soda all over the laser. Whatever, you know, things happen. And so people don't want to show that, so therefore they don't want to have their data available. Maybe they also don't want somebody to come back and reinterpret and interpret that they misinterpreted the data because they make them embarrassed. So it's sort of like changing our attitude to be a scientific attitude that we're trying to really figure out what the truth is a key psychological thing to work on. And part of it is trying to give people incentives to do it. So it takes time to take your data, get it into a format that's actually useful for somebody else later. You know, save it up carefully and look at it, you know, each data and think about it. And usually people are, by the time they have it ready to publish, the student's already ready to file his thesis and has a job lined up and is in a hurry and doesn't want to spend the time to do it. And, you know, so there's a lot of like psychological incentive factors that you need to work on. But for science, it would be really great to be able to do it, to be able to save all the data we have and reinterpret it as our knowledge improves. And then what's happened instead, so this is what I think would be the smart thing, but unfortunately it's not the reality. The reality instead is that people publish a bunch of papers about some reaction, and then a few years later, a committee is formed called the evaluation panel, and then they read all those papers, look into what's known now about it, try to reinterpret as best they can with the limited data that was published, and then try to write down, this is our cumulative recommendation from what's known today, given everything about what the real value is, and what the real error bar is. And so I want to talk a little bit about how you can read those papers. So this is one of those evaluation panels, a very important one for us. It was the evaluated kinetic data for combustion modeling. So that's very important. And this is a multi-part long paper. This is the second supplement. It's like hundreds and hundreds of pages. And this guy Bouch from Leeds was the leader. Tom Bowman, a professor in mechanical energy at Stanford, was one of the main authors. And there's a whole bunch of other authors. And this is in the Journal of Physical Chemistry reference data. So this is a journal that specialty is trying to publish really good numbers with error bars. This is headquartered at NIST. NIST is one of the few places in the world that really cares about error bars. And so they really try to publish. They have a whole journal that's just about error bars, really. So just I'll show you a typical thing. So this is for this particular reaction, O atoms plus OH to go to O2 plus H. So this is the reverse of the main combustion reaction. And this reaction, if you look in their data sheet, they have first thermodynamic data about it. So they'll look up the very best thermo for all these guys. And in this case, these are all in the active thermochemical data table, so the numbers are really good. So they have really good numbers. This is the entropy, best they know. Then they compute the Kc for you, write it down, and they fit it to this form. So this is a fit to the Kc derived from the free energy from the delta G there. So that's the top of the table. And then they have a summary of all the literature that they found that the committee looked at. So there was 1, 2, 3, 4, 5, 6, 7, 8, 9 different papers that reported rate coefficients for this reaction measured. And then there were 1, 2, 3, 4, 5 papers later that either reviewed or evaluated some of this data in the past. So here's like a little bibliography about it. And then they have little footnotes about each thing. It says about how they made the measurements, what they did, what things you should know about those numbers. And they also tell you the temperature range that it was measured in. And you can see a lot of times rate coefficients are only measured at one temperature. Because sometimes the rate coefficient is not the main purpose of what the purpose was trying to measure. So they're trying to do something else. And by the way, we know we were able to measure this rate coefficient, but they didn't really care about us. They just measured at room temperature or whatever was convenient for them. So there's you see a lot of these are just at single temperatures. And then once in a while, you get somebody who tries to do a range. And then you always have a limited range because it's the range of what their apparatus can do. Sometimes when you make the temperature range too much, a side reaction starts to take over from the main reaction you're trying to observe, and so you can't really do the experiment anymore. So these are some of the footnotes for this particular reaction from this table. So footnote E says that for this particular paper they're talking about, it was measured using a fast flow system where they first made O atoms by running a reaction upstream. The O atoms were flowing downstream, and then they seeded a tiny bit of nitric acid into that stream, and they flashed it with a 266 nanometer photons and made some OH. And then they measured the disappearance of the OH by laser-induced fluorescence. And then, so this is, to somebody who's an experimentalist, this basically tells you a lot about what this experiment is, and you don't have to read the whole paper to get a rough idea of what they did. Then here they'll say that this other number, this one came from looking up somebody else measured rate coefficient, and then they used the KC from their thermo. Now, in light of what you guys know, that the value of thermo of OH radical changed. Do you remember in the 2000s? So you might be worried about whether this is really true or not. So you might look and see what value they used to do their KC. And this one is another one where they actually took some rate coefficient from somebody else, and then they also used some thermo and tried to glue something together. So this is like very secondary. This is not a primary source of information. This is like a refit. And then the committee will write down in the paper, we recommend this preferred value. K should be 2 times 10 to the minus 10, T to the negative 0.352, this exponential, these units. And they'll say what range of temperatures they think it's good. And then they'll also say what they think the error bar is in this K. And they'll usually give it as the expected error in the logarithm of K. So they think it's plus or minus 0.2. All right. So some comments about this. In this case, all those numbers, those measurements of that reaction were all low temperatures. You saw I think the highest temperature is 515 K. So they're all very low temperature compared to combustion. And it looks like that they agreed with each other. The numbers are pretty close. So that number is well known, but it's only known in a certain small temperature range. But then the reverse reaction has been measured a lot at high temperature, because that's very important for combustion. And so then you can use the relation between K forward and K reverse in the thermo and extract this. And here they say they computed the preferred expression by combining the forward rate and the reverse rate with the thermo to get one expression. And there's a bunch of theoretical studies, and they recommend you go read these papers by the theoreticians who tried to figure out this reaction. And then they make a plot of their recommendation, which is this line, versus the experimental points. And you can see experimental data points. This is log plots. This is probably 1 factor of 10 here. And so this is very typical of what you see. So, the experiments don't agree with each other that precisely, so they're sort of scattered a bit. And of course, this committee drew its line right through the points, basically, because it's trying to make some expression that looks like the data. And it's not based on any real theoretical basis, it's just a fit to them. All right, and then the reverse reaction, you can read about what they said about that. And they give you a different recommendation here. And they plot it. And there's their line that they drew through all the points. And this one's such an important reaction that a zillion people have measured it at a lot of different temperatures. And what you can see from this is that the measurements, they don't agree, but they're sort of in the same ballpark, right? So a lot of people try to measure this. They all have error bars a little bit different. They have different systematic errors. So they're not quite exactly right, but they're all these measurements, mostly pretty close. You see something happened to this guy. He's off. But mostly it's pretty good. The scale here, this is 4 orders of magnitude from here to here. It's a log scale. So rate coefficients vary tremendously with temperature, and it's really easier to talk about logarithms or rate coefficients. It's maybe a better way to think about it than the absolute numbers. And so they plot the logarithm. The logarithm, it looks like a nice straight line. Everything's looking pretty good. But of course, even these little errors are pretty big because this is such an expanded scale. And you get this idea, there's like a sort of a cloud of points in here. So there's sort of like a probability density function. Does that make sense? It's like, what is the real value of the rate coefficient? Well, it's probably somewhere in here, but I don't know exactly. And you get an idea sort of how wide that range is of uncertainty. So this leads to the question of how do you represent the uncertainty? So a lot of times people would do is they would just quote a number, and then they'd quote an error bar. And many people would read that and assume that that means that there's a Gaussian distribution of errors, a normal distribution. And a lot of times people might say that assume the error bar is equal to 1 sigma. Right, because that would be the simplest thing. 1 sigma error bars, and it's a Gaussian normal distribution. But this is usually not true. So if you see a number and an error bar, you have to read what the person meant when they made it. So for example, in some fields, quoted errors are always 2 sigma. This is pretty common in kinetics. If you experimental kinetics, you usually report 2 sigmas instead of 1 sigmas. So the error bars are twice as big as you might think. And in thermo, it's always 3 sigmas. So you have to just know that. If you're in the field, there's certain conventions in the field. And the convention for thermo is they use bigger error bars, so they really want to make sure that there's no possible way that the number could be outside their error bars. Another possibility is you can just say, I am absolutely sure the value is not outside this error range. So draw such a big error bar that you are positive there's no possible way it can be outside the error bar. So that's called an interval. You're not really sure what the number is, but you're definitely sure your limits. This can't possibly be. And sometimes you can be sure, like for kinetics, you know the rate coefficient can't be negative. So you can put your bottom of your interval 0. Definitely k is bigger than 0. And actually, you know that the k can't be faster than the diffusion limit. So you can put the diffusion limit at the top, and now right away you know the error bars on any rate coefficient, right? All bimolecular rate coefficients are right in that range, and so the whole challenge now is to try to make that range a little smaller. And in general, people have come to the conclusion it's best to report everything in log k. So because the reason is, one thing is that the k has to be positive. If you just have a k plus or minus something, it's easy to have k plus or minus something, and people might infer that you think that the k could be negative, because the plus or minus could be so large. So that's totally stupid. It can't be. So if you do it in log k, then at least it's just scales. And then also, it turns out that both in the experiments and also in the calculation, there's a lot of different steps that are prone to multiplicative errors, but there's not really things that are prone to additive errors. So when you measure a rate coefficient, for example, by the pseudo first order method, your error is often dominated by a calibration on the other gas. Let me see if I can explain this. So what you usually measure is you measure 1 over the exponential decay time versus the concentration of the reagent y that you're reacting with. So this is for x plus y. It goes to something. You're measuring loss of x. You measure the time constant for the loss of x. When you increase the concentration of y, the decay gets faster. So if you plot it this way, this often looks like this. And then what people do is they say that the k for this reaction, k for x plus y, is equal to the slope of this line. And then you measure for a bunch of different individual concentrations of y, and then you fit a straight line fit. That's the most common thing to do. This whole thing relies on your ability to measure y. And if you have, say, a 5% error in one of your mass flow controllers, you might be 5% off systematically in y. And that systematic error would come into a systematic error in k, because the slope is delta of this over delta of this. And if your scale here is off by 5%, then your delta will be off by 5%. So it's a multiplicative error. It's not a plus or minus on k. Does that make sense? So that's the most common thing in the experiment. The same with quantum calculations. If you looked at that formula for k of t with conventional transition state theory, you have a lot of things multiplied together. Some q's, some exponentials, all these things. And all those things, there's easy ways you could have errors that are multiplicative errors in those things. And so oftentimes you have errors of sort of factors of 2. It's not plus or minus something. So log k is better. And this immediately makes you think, if you think that the error, let's see if I can draw this well. So, the naive way to think about this is I have k, here's the nominal value of k, I have a Gaussian distribution about this. So one problem here is that this scale goes to 0, so there's a tail of this Gaussian that's all the way down here is negative, which is unreasonable, right? But now I'm telling you that actually you do better if you use log k. So in a log scale, the error will look different. It'll be like, if I had it, well, really I should make this log k nominal. And now I have a Gaussian for this. And then if this is the number that was reported by the Bouch committee. Delta log k is about 0.2. That's what they said. And so then you could transform it back into k-space if you wanted to see what it looked like. And I think what it does is it would go, it makes this more sharp on this side, and then it goes out further on this side. Something like that, if you transform this into that. So in k-space, this is not Gaussian, even if it is Gaussian in here. And it might be Gaussian in here. However, this is only if you had multiple measurements by multiple different people. If everybody was measuring it using my same mass flow controller that's off systematically 5% all the time, then they're all going to be 5% too high. And they're not going to be both too high and too low, right? But if you have a case like this, where there's 27 different groups did it, then presumably their systematic effects mostly it might be some positive, some negative, you might hope, unless they all reproduce exactly the same error, which also happens sometimes. If it's a tricky systematic error, maybe they'll all make the same mistake. And then there's another very important thing, is that in the tables, you'll often read, if you read the footnotes, they'll say that the value of k that reported is not actually the true value of k. Instead, it's the inferred upper bound. So sometimes they can prove that the rate must be really slow, but they can't tell how slow it is. And basically, this says I couldn't observe it happening. So they put x and y together, and as long as they could wait, x and y didn't change their concentrations. And so then they'll say, well, therefore, we were willing to wait all day. We saw nothing happen in a day. Therefore, the rate of x and y has to be less than something. If you read it in the tables, it says that, but a lot of people might just see the number and just take it and use that as the rate. And so now they're using the upper bound as the true value in the model. Sometimes there's two competing values. So there might be several people who say that the rate is such and such. There were several people who say, that, like with me and the other guy in the Nature Chemistry article. So I have one number. It's a factor 10 slower than his number. We both quote tight error bars on our numbers. The error bars don't overlap. So one of us is right, one of us is wrong, or maybe we're both wrong. We're definitely not both right, right? And so in that case, if you were looking at the probability distribution, what it should look like, in our case, is here's my measurement, and then here's his measurement. And I don't believe his measurement, so I'll give him his lower probability of being true. But there's definitely some probability he's right, some probability I'm right. And if either of us is right, probably the real error bar is small because we spent a lot of time trying to figure out the precision of the reported error bars. But if you had no idea which of us to believe, then you might just write the probability distribution function this way. But this is a little bit harder to represent than just a single Gaussian.
What are you supposed to do? Like if you go through the GRI mechanism, a lot of the CO oxidation, you'll have just an A factor. And you may or may not be able to find a paper regarding that rate. How would you treat that for uncertainty? Because I know that there has to be a temperature dependence.
Yeah, so in many times when people try to figure out the uncertainties, it's mathematically more convenient just to worry about the errors in the A factors. So a lot of times people just assume the EA is perfect. They lock it at the nominal value. But of course that's ridiculous. What you should really do in that case, to figure out what you can say about that is pretty tricky. So you'd have to go and look and see when they inferred that error bar in A, was all the data at one temperature? If it's one temperature, it's really an error in K. And you don't know which of the A or the EA is inaccurate. If it's at multiple temperatures, then maybe if you look into detail, you could see that you have a bigger error bar at some temperatures and a smaller error bar at the other temperatures. And then you could kind of infer a separate error bar for the EA. I'll talk a little bit later about the problem. Generally, the errors in EA and the errors in EA are highly correlated because usually we only have data in a very limited T range. And so there's a guy named Charan, he's published a lot of papers about this, trying to figure out what we can say about the error bars separately. But currently, right now, we usually don't know the error bars very well, I would say. I'll show you how they did it in the committee here in a minute. Another important thing is if you notice in that table and the recommendation, they were using the KC a lot. They were using some forward rate coefficient for the forward reaction, but they were also using a lot of information from the reverse reaction and using the KC. So then if there's an uncertainty in the KC because there's uncertainty in the thermo, that's all propagated in to what they did. And so that will tend to often give very non-Gaussian things. So in this particular case, all the low temperature data was from the forward reaction. All the high temperature data was from the reverse reaction using the KC. The error in KC will systematically move all the high temperature data up or down, depending on what that error is. And so that would change your EA sort of directly, because the low temperature data are almost all at the same temperature, basically. So it's just like a point. And then you have this lever arm of all the high temperature data, which has this extra uncertainty due to the KC, as well as whatever errors it actually had itself at high temperatures. And now you remember that this reaction was measured by Hong, like 2010, 2011. And these measurements are after the committee report. So none of this data was included in the committee report. And Hong, he went back and he took several of the previous data, but not all of them. And then he did his own best fit. So he disagrees. I don't know if it's he. Actually, I don't know if Hong is it he or she. I'm sorry. I apologize to Hong. But anyway, Hong did nice measurements, and here they are. And it has a very beautiful fit. And now the tightest error bars on this reaction that are reported are from this. And they seem to be pretty consistent with other people's measurements. But the committee never looked at this because the committee was over before they got around to doing this experiment. And then later, Burke did some other sort of indirect work which supports the Hong rate coefficient. So I think currently people think the Hong number is right.
So this is absolute value of K or log K?
100%. So my opinion would be it would be error in log K of whatever the log of 10% is. But that's a good question. And I don't know if Hong meant 1 sigma, 2 sigma, 3 sigma. I have no idea. You'd have to, hopefully in Hong's paper they clearly say what they mean, but I'm not sure. So that's a good question. Now if you look at this number, for example, the EA is 7670. Hold on a second. Just this. Hold on. And these guys said 7560. So you can see the EAs are not the same. Sorry. Question, yeah.
So can you elaborate more on where does the uncertainty in thermal come from?
Uncertainty in?
Thermal, like KC?
Sure, yeah, where does the uncertainty in thermo come from? So the thermo for stable molecules, a lot of it's from heats of combustion. So the way heats of combustion is you weigh out some of your fuel, you put it in a closed container with air or oxygen, and then you have a little spark, light it, and you let the whole thing burn up, and you have it usually sticking in a container full of ice, and then you measure how much of the ice melts. And that'll be the heat that was released by the reaction. So how precisely can you measure the weight of the fuel you put in? How pure is the fuel that you put inside? How accurately can you measure how much ice melted? How much heat gain or heat loss was there other than between the stuff and the ice? So all those things could be a couple percent. And so you can get several percents of error. Also, that heat of combustion is like measured basically at the ice temperature, whatever the temperature is at the end, because you put it in at that temperature and you measure it, take it out at that temperature. So then you want to extrapolate up to the real combustion temperature, you'll get, or the real temperature where you're going to compute the KC. That relies on estimates of the heat capacity, which probably come from statistical mechanics, which have to do with estimates of vibrational frequencies. And often some of those are measured and some are not, and they all have error bars too. So the heat capacity is not known precisely either. So you can propagate through all these errors. So each of them in those cases, those are all small, so maybe a few percent. But there's a lot of them. And so if you propagate them through carefully, you'll get some number. For the free radicals, it's a lot more complicated because usually they have to do several different reactions that make the free radical, or photoionization events or other things like that that make the free radical. Each of those have a whole bunch of errors. And so the active thermochemical table people found out that what you should do is take every known reaction that involves this radical that has some thermo information or equilibrium information or photoionization information and put them all together. And then the error bars are like, they're not correlated very much because the measurements are done in different ways. And then you can actually, by the combination, get the total error bar to be much tighter. Yeah. So is that okay?
Yeah.
Another question somewhere? No? Okay. All right. All right, so the H+O2 one I showed you is a case, an unusual case, where there's more than 20 different research groups who tried to measure that rate coefficient. So that's a case where we have like a statistical sampling of different measurements. Much more commonly is a case like this, where here are the total number of measurements, 1, 2, 3, 4, 5, 6, 7, 8. You can see that 1, 2, 3, 4 of them are at room temperature, and the other 4 are at really high temperatures. So we only have 4 numbers, and there's no spread. So there's a gap between 300 Kelvin and 1300 Kelvin where there's no measurements. So that whole intermediate range, we really don't know what the rate coefficient is. And then the high temperature measurements, which is these shock tube measurements, it turns out all of them had to use mechanisms with several steps. Okay, so what that means is that they fitted a very complicated differential equation model with couple differential equations, and they tried to vary the rate coefficient for this one step and hold all the other rate coefficients fixed at what the nominal values were from the literature on those guys. But all of those guys had error bars too. In fact, some of them might even be wrong. So this whole procedure is very fraught with possibility of being wrong. So the fact that this is actually Professor Pilling wrote this slide. He was on the panel, so that's why he knows about this. And he said, not possible to correct for more recent values, emphasizes the need to store raw data to allow accurate reevaluation. So at least in his opinion, he doesn't trust that the old groups that did this in the shock tube correctly interpreted their data. So that means he basically doesn't believe any of the high temperature numbers. So that really cuts it down. All we have left are points at 298 K. So we have one temperature point that we can believe. And there we can look and see, well, this is 2 times 10 to the minus 10. This is 1 times 10 to the minus 10. This is also 1 times 10 to the minus 10. This is 5 times 10 to the minus 11. But then he says that the way these guys interpreted their experiment, they assumed a certain value for this reaction. But that was way back in 1975. And at that time, people thought that reaction had a different rate coefficient than they think it is today. So if you reanalyze their number, you would actually get instead, you would get 7 times 10 to the minus 11. So we're left with 1 times 10 to the minus 10, 2 times 10 to the minus 10, and 7 times 10 to the minus 11 as the 3 values that exist that the committee had some confidence in. So this is a problem. So then they say, boy, we have no idea. So the committee recommends just using this number, no EA, no T dependence, just this number, which is somewhere right in the middle of those experimental numbers that I just told you. And they say, well, we'll use it everywhere. Close to 298K, we have a quite tight error bar, maybe a factor of 2. That's what a log error of 0.3 is about, a factor of 2. But who knows at high temperature? Says the committee just said, well, we don't know, but let's just make the error bar bigger since we're not sure. And so they all voted, what number do you like? 0.7, 0.8, 0.6. And there's a majority of the committee voted for 0.7. That's what they published. That's here. All right. They also comment that the reaction is presumed to proceed via an ethyl radical adduct. So they know the experiments measured the loss probably of the CH2, but they didn't say what the products were. So this makes the whole interpretation very confusing because depending on what the products are, you might have secondary chemistry of the products coming back and doing something, but if you don't know what they are, then it makes it harder. They said that everybody presumed that it made this ethyl radical. And if so, from the kind of argument that we did on the board yesterday, you would expect it would have a very weak t-dependence. So they said, if that's really what the product is, probably has a weak t-dependence. That's why we'll just give one number with no t-dependence. That's the way they thought. But they're not really sure what it is. So, but they say there's scatter at high t, and provisionally, we recommend this. Okay, so provisionally, that means they had no idea. Okay, but you need a number, right? Because you're making a model. This is a reaction. They measured it. It actually happens. And at least at the room temperature, it's pretty fast. So probably it's still pretty fast at high temperature too, but they're not sure. This is a reminder of the forms for the pressure dependence. So this is the TROA form for a simple case of pressure dependence to do the fall off. And so here's a reaction. And this is one where people have tried to measure at low pressure, at high pressure. And then the committee analyzed it and recommended an error in the low pressure coefficient, a high pressure coefficient, and an error in this F factor, which is the factor that controls the shape of the knee between the low pressure and the high pressure. So here's the knee. You see, here's the low pressure number, the high pressure number, and actually, it looks like almost all the data are measured in the region of the knee, making it kind of hard to extract from them what the real high pressure limit is or the real low pressure limit. And you can see it doesn't really exactly match. See how this is kind of going off like this, but the theory says it should be like this. Who knows? So if you ever get the joy of being on a data evaluation panel, this will give you an idea of the problems you'll face, is that you'll have these data points, and now you have to tell the world what's the rate coefficient. And you have to give it some expression that works over all t and p. All right. Another issue is this covariance of uncertainty. So as was mentioned earlier, the A factor and the EA are almost always covariant. I mean, you have an uncertainty in the rate coefficient, and you also have an uncertainty in the temperature dependence, the rate coefficient. And it's hard to figure out how much of the uncertainty is due to one and how much is due to the other. And they usually have an extremely high correlation. If you do fits where you let A and EA vary freely to try to match some data, almost always you'll find they have like almost perfect correlation, that if you choose a high value of A, then you should choose a high value of EA to make the rate get smaller. If you choose a low value of A, you can get a good fit by using a small value of EA also. So you have a very correlated system. That screws up a lot of your normal assumptions about error propagation. Do you know if you, normally we assume uncorrelated errors, uncorrelated parameter fits, stuff like that. This is a case where it's almost completely correlated. So you're completely wrong to assume it's uncorrelated. So because of this, Tarani, his group has been working on trying to figure out better ways to represent the rate coefficients in a way that would remove the correlation. So you'd have more uncorrelated parameters. And then that would make it simpler to understand what's going on. And so they did a study of the reaction of O plus ethylene. This is another really important reaction because most fuels break up to ethylene by the beta scission reactions we talked about before. And then you make a lot of O atoms from the combustion reaction, H plus O2. And so usually these guys are both in pretty high concentrations, and this is a really important reaction. And so because of that, a lot of groups have measured it. So we have a pretty good t-dependence, but you can see it's not a straight line. You see it's non-Arrhenius t-dependence. And so the committee recommended a certain error bar at low temperature and then a higher error bar at higher temperatures, and some goofball t expression there. And over only a certain range. Actually, they only recommended up to 2,000 Kelvin, so 25. So I think that they didn't believe these last few points here or something. They weren't sure, so they just said cut off the parameters there. Sorry, I'm going back to the wrong reaction. So if you have a t-dependence, okay, so to fit that shape, it's non-Arrhenius, it's curved, so I have to have a t to the n. So now I have three parameters, A, n, and e. And then I can do analysis of all the data and get a covariance matrix of the error uncertainty in A, N, and E, and then the cross uncertainties between all of them. And then you can do uncertainty propagation from the covariance matrix, if you guys look up the rules about how to do this. And this is what the formula is. It's come really strange t-dependence of how the uncertainty should vary. And so for this particular reaction, Tarani group did it. The the panel, the Balch committee, recommended an error bar like this, and then a bigger error bar in the middle because there was no data, and then a different error bar at high temperature. Do you remember we had high temperature data that was relatively uncertain. We had low temperature data that was pretty solid, and there was no data in intermediate temperatures. So where there's no data, the committee said give a bigger error bar since they had no idea. And then Tarani said, well, let's try to take care of the covariance and stuff, and they recommended a different, this dotted line shape with the errors kind of, they don't think the error gets so big in the middle. I think that's what Tarani's saying. They also tried to do this for the H+O2 reactions, which is really important. And this is another one where you get a lot of correlation. So if you just look at Arrhenius plot, it looks okay for H+O2. But if you look at it for H+O2 making HO2 as a product, it has a pretty strange curvature here. It gets less important at high temperatures. The rate gets slower at high temperatures than at low temperatures. So this is inverse temperature dependence, and also non-Arrhenius in the shape is curvature. And there's a lot of data, I think, in this region that are pretty solid, but then it gets pretty uncertain at high temperatures because it's hard to see it because the rate gets slower. And the other reaction, this reaction is taking over. Almost all the flux is going that way. So the Balch group, just being guys in the committee voting, they just said, okay, it's a small error here and it's a bigger error there, so let's just draw a straight line between the two. And Tarani tried to do a fancy analysis with the correlations removed and everything, and he thinks that the error bar is actually smaller. Because by taking away the correlation, that removes a lot of the variance. And then to do that, they actually had to now have 5 parameters. And so you have the correlations between all of them. And you can see some of these off-diagonal correlation terms are very close to 1. And so that's the problem with using this representation. That's enough about that. All right, so this all leads to the problem. So the experiments alone have a limited ability to really nail down what the numbers are. And so one option is to do more experiments. And so that's what Hong did. So Hong did the H+O2, lots and lots of experiments. I think there's like 4 journal papers, many, many data points, lots of work, and they're able to nail it down. But most people are lazy. They don't want to do that much work. It might be hard for them to do the experiments. Maybe there's certain temperature ranges where it's not practical to do the experiment. So it would be really nice if we could supplement the experimental data with quantum chemistry data. And then we could understand and then we could use it. We had that extra information. We had the quantum chemistry. Somehow we should be able to combine that with the experimental data to get a better estimate of what the real values are. The problem is that nobody really knows how to do is what's the uncertainty? And the problem is we don't really know what the uncertainty is in the quantum chemistry numbers to start with. So therefore, we don't really know how to combine it correctly with the uncertainties in the experiments to get an overall uncertainty in the combined prediction. And a key thing to keep in mind is that most of the error bars are estimates not really rigorously determined by doing standard deviations and stuff like that. Because usually we don't have that many repeats of anything to determine anything by standard deviations. And also, a lot of the errors are systematic. And in the quantum calculations, they're all systematic. So for example, most of the A factors, entropies, and heat capacities, and also zero-point entities are all derived from second derivative calculations using DFT. And the DFT is based on some approximate energy functional. And we don't know what the error is in that approximate energy functional relative to the true functional. And since all we know is the existence proof, right, for the true functional, so there's no way we can figure out what that is. So we don't know how big the error is in all these numbers. However, by experience, comparing to experiment, for a lot of cases, it's a pretty small error. So we love to use the DFT. We can calculate it. Usually it's pretty good, but we don't really know what the real error is. And then in calculations for the higher level methods for calculating the energy differences, and also in the procedures that we use to calculate the Qs, for example, how to handle the inharmonicities, we have a lot we know we're making approximations, but they're not controlled approximations in the sense that we don't know how to bound how much error they could introduce. So from experience, a lot of times they're good approximations, so we use them. But most people aren't willing to do the work to try to actually to put a bound on what those approximations are. So we just end up with a nominal value with the approximations in it, and we don't have any idea how accurate it really is. So That's a problem. And then also, all the methods use basis sets. And in principle, you should go to the infinite basis set limit, where you just put more and more basis functions in. But people get tired of doing that pretty fast. Just like in the CFD, people get tired of using finer and finer meshes, right? In principle, in CFD, you should repeat the same calculation with a finer mesh. And, maybe you find a paper they did it once. You never find somebody who keeps grinding the mesh until it's they're guaranteed it's really converged. And it's the same thing with the quantum chemistry. They'll use 2 basis sets. If they both give about the same result, they say, oh, good enough, I'm done. So because of this, we're really in trouble that we have all these errors that we don't really have very firm numbers of exactly how big the error bars are. And so we're in a quandary of how to proceed. And more and more, most of what we have in kinetics now is coming from quantum chemistry, not from experiments. And so we're really relying on the quantum chemistry a lot, but we really don't have good error control of it. And then the experiments, for most cases, we don't have very good control either. Despite the efforts of the evaluation panels and the experimentalists, there's so many reactions, and people just don't repeat the experiments a lot, and it's just not practical. So it's very important to figure out how to combine them as best we can. And there's some recent work. The Argonne National Lab has a group of kinetics that works on this kind of stuff. And these 2 people in particular, Michael Burke and Alison Tomlin from Leeds, who was visiting at Argonne, they've both published papers on recommended procedures of how to tie together the quantum chemistry with the experiments in order to try to get unified error bars that you can believe. But this is like very early days. So there's like maybe a total of 5 papers about how to do this. And it's definitely not, you can't just buy Gaussian and look in the output deck and see the recommended error bar. There isn't one. So it's still a long way to go before it's really routine. Okay, let's stop and take a break, and when we come back, we'll talk about reaction mechanisms.